morning, students. In continuation to electric dipole, last class we discussed about the torque on an electric dipole. Today there is a very important concept which we are discussing regarding the electric dipole is potential energy of a dipole in an uniform electric field. So what will be the potential energy of a dipole in uniform electric field? You know that this was the electric field and there was a dipole, remember, plus q minus q, and this was the angle. Now dipole can rotate from one angle to the other angle on either of the direction. Say this is plus q minus q, okay, say theta 1, theta 2. It can be against the electric field, it can be along the electric field. So when it rotates, it walks. So how we are going to derive the expression which comes for the potential energy is U equal to minus PE cos theta 2 minus cos theta 1. Now how it comes, I'll derive it. Let dW is the work done. Remember, dW is the work done for d theta rotation. In 11th, usually we say dW is the work done for ds displacement. It's a rotational motion, that is, it's an angular displacement. So dW is the work done for d theta rotation. So what is dW? dW will be equal to torque d theta. Now already we know torque. What was the torque in this case? Remember, it was PE sine theta d theta. You remember the torque was PE sine theta. Already we have derived it. So this is the dW. Now just we will what net work done. So we all know that for net work done, okay, integrate first theta 1 to theta 2. So the net work done was integration of P sine theta d theta, theta 1 to theta 2. Now all of you know that W P will be out, and what is the integration of sine theta? It is minus cos theta, theta 1 to theta 2. Finally the minus, it comes out and it is P cos theta 2 upper limit minus cos theta 1. So this is the work done. And do you know, this work done has a form. Always a work done can be stored in the form of energy. So work done is stored as what? As the potential energy of the dipole. So potential energy of the dipole. So finally we can say that this work done can be written as, you know, that U equal to minus P cos theta 2 minus cos theta 1. So theta 1 is the initial angle, theta 2 is the final angle. So this is the work done, and we can see that how it rotates and how the work done. So this is the second derivation after the torque, the potential energy, how a dipole rotates, and it's a rotational displacement. Now if U is equal to, okay, we can write even in this way P, and we have taken minus inside, so it can also be written as cos theta 1 minus cos theta 2. So this is another form of the orientation. And if we say theta 1 initially is 90 degree, the dipole was perpendicular, and theta 2 is what? It is say 0 degree or say theta, any angle. So what will be it? You know that it will be minus p cos theta. So in this case, it can be written in this form. So minus pe cos theta. And how many of you know that it can also be written as minus p dot e? So this is the another case. Sometime it is given that theta 1 initial is 0 and final is 180. So what will be in that case? P, that is cos 0 minus cos 180. So I think all of you know what is cos 0 is 1 and here cos 180 is minus, to minus minus plus. So it becomes what? 2 PE. So this is twice of the PE. So this is the maximum work done in this case. Maximum work done, maximum energy. So there can be cases, one is this and the other is this. Okay, so this is how we explain the potential energy. Now there's one numerical I'm going to explain based on this potential energy of the dipole and how we are going to calculate it. Say it was asked in board and it was asked in thrice, three times, 2004, 2006 and 2000 what 14. What is the question? I'm going to write it in a short way. An electric dipole, an electric dipole of length 4 centimeter, that is dipole length, and placed at an angle of 60 degree, at an angle of 60 degree with electric field, with electric field experiences, it experiences a torque, experiences a torque, experiences a torque, and the value of the torque is given 4 root 3 Newton meter. Okay, and what has been asked? Calculate. One is the magnitude of electric field and second is the potential energy of dipole. Okay, and what is the given? Charges are given, the charges are plus minus 8 nanocoulomb. So this is the question, and this is formula based question, very simple. You know that what has been given. First we'll see that what are the things given here. The length is given 4 centimeter, the angle is given 60 degree, the torque is given 4 root 3 Newton meter. So these things are given here. It is the way how we are going to find out. And I think all of you know that what was P dipole moment Q into 2A. So Q is what? 8 nano, 8 into 10 to the power minus 9, and 2A is in centimeter. We can write it in meter 0.04. So calculate it. 8 4 is 32. So it becomes 0.32 into 10 to the power minus 9, and this is coulomb meter. Now we can calculate both the, what is the torque? P sine theta. So we want to calculate E, it will be torque upon P sine theta. So we will put the values 4 root 3, what is P? We have calculated 0.32 into 10 to the power minus 9 and sine 60. So put the values here, 4 root 3, 0.32 into 10 to the power minus 9 into what? Root 3 by 2. And this is the value given. So solve it out, and when you solve it out, it comes 2.5 into 10 to the power 10 Newton per coulomb. So just you have to solve it out. And what is the second thing is the potential energy. U is what? Minus P cos theta. So minus P cos theta 0.32 into 10 to the power minus 9, and E is already you calculated here 2.5 into 10 to the power 10 and cos 60. Okay, so calculate it. that is 10 to the power minus 9, and 2.5 into 10 to the power 10. What is cos 60 is just half. So calculating it, it becomes what? Minus 4 joule. So calculation you can check. So this is how we are going to use the formula for an electric dipole. This question was asked in 2004 and 6 and 14. So this is the question related with an electric dipole. Now further we are going to talk about the dipole. We'll move on, and there are two very important things related with the dipole. And what are those? Do you know that we can calculate the electric field due to a dipole? So there are two another derivations. Electric field at an axial point of a dipole. Now there are 2 points. One is on the axial axis and another is on the equatorial axis. So what we are going to talk, have you heard about the axial and equatorial? If you see a bar magnet, I will make a separate diagram. This is a bar magnet. Do you know this is a equatorial axis, this is a axial axis. This is equatorial, this is axial. Same is with the dipole. If you see a dipole, say this is plus q and this is minus q. Okay. And this is the center of the dipole. This is 2a, this is a, and there is a point on the axial line. So we are going to calculate the electric field here at axial point. Now this dipole plus q, if you see plus q, the direction due to plus q will be away. So it is E1, and due to minus q, it will be towards. We know that the electric field lines, they move away from positive and towards the negative. And this is, say, distance r from the center. Got it? This is the dipole. This is a point on the axial line from positive charge away from negative charge. E1 is from positive charge and E2 is from negative charge. And I think all of you know that this is plus q, this is minus q. We can interchange also. We can take minus q on this side and plus q on that side. We can do that also. So if you want to take in the reverse way, you can take in the reverse way also. And here E1 is this, so E2 is greater than E1. Got it? So net E will be E2 minus E1. So this is how we are going to calculate. Now what is the electric field? E1 due to what? With charge? Plus q charge at P. So E1 will be, what is the electric field formula? KQ by R square. So KQ by, from here distance will be R plus A. So R plus A whole square. And E2 due to minus Q charge at P. So E2 will be, I think you know this distance is R, so it will be R minus A. So KQ R minus A whole square. E1 is away from charge and E2 is towards minus Q. This we know that. E2 is towards and E1 is away. So net electric field intensity. Now net electric field intensity on axial line will be E equal to E2 minus E1. Why? Because E2 is greater than E1. Already we have seen it. So what is E2? It is KQ upon R minus A whole square, and it is KQ upon R plus A whole square. And then what happens? KQ's out, and you can see that you can take it here, and then finally KQ, I can write here directly R square minus A square whole square, and if you solve it, R plus A whole square here, and it is R minus A whole square here. Solve it out. I am going to write it directly. it will be 4RA. So R square minus A square whole square. And finally, KQ, it can be 4RA can be written as 2A into 2R. R square minus A square whole square. What is Q into 2A? You remember, it is P, dipole moment. So finally, E can be written as Kp2R upon R square minus A square whole square. And what is the value of K is 1 upon 4 pi epsilon naught 2PR upon R square minus A square whole square. So this is the concept for axial line. Now do you know, generally in the board they ask for the short dipole. For short dipole. Now what does it mean by short dipole? Short dipole means the length is very less. That means A is less than R. The dipole length is less than the distance. So what happens? We neglect A square. You know the binomial? A square is neglected. So finally when A square is neglected, we can write 1 upon 4 pi epsilon naught 2p by what? It will be R, and it will be R square, R to the power 4. Then we cancel it. So it comes 1 upon 4 pi epsilon naught 2p by R cube. So this is the electric field due to short dipole. And here very interesting thing is that E is inversely proportional to RQ. For a point charge, it was inversely proportional to R square. Now this is for the axial line. Now again we will talk about the electric field intensity due to an electric dipole at a point on equatorial axis, equatorial line. So now we'll talk about the equatorial line. Okay, so if we see, this is minus Q, this is plus Q, and this is the equatorial point P. This is A, total distance is 2A, and this is R. What do? We join them from this end, and we join them from this end. This is plus Q, so electric field will be away, say E1. This is minus Q, electric field will be towards E2. This is also theta, this is also theta, and this distance is root R square plus A square. Okay, this distance is again R square plus A square. And if this is theta, do you know, this will be also what? Theta. So this component can be written as E1 what? Sine theta, and this can be written as E1 cos theta. You remember components of the vector. Same is E2 is in this direction. This is also theta, alternate angles, so it can also be written as E2 sine theta, and here it is E2 cos theta. So this is the case, plus Q minus Q. E1 is away from the plus Q, E2 is towards. E1 has two components, and E2 is also having two components. So this is how we are going to start. So E1 is the electric field intensity due to plus Q at point P. So all we know that E is KQ by R square, so KQ upon root R square plus A square whole square. So it becomes what? E1 is equal to KQ upon R square plus A square. And E1 is directed away from plus Q. Okay, plus Q. So this is one equation. And similarly, you see that E2 is the electric field intensity due to which charge? Due to minus Q. We take always magnitude here at point P. So the magnitude will be same. KQ, the same thing will come here, root R square plus A square whole square, direction is towards. So E2 will be KQ upon R square plus A square. This is second equation. And E2 is directed towards what? Minus Q. And main thing is that the magnitude are what? Same. E1 is equal to what? E2. So what will happen? E1 sine theta and E2 sine theta cancels out. So E1 sine theta and E2 sine theta cancel out. Why they cancel out? Tell me. Because they are equal and opposite. So equal and opposite. Only cos theta component works going to this direction. So net electric field intensity, okay, at point on equatorial line. So I think got this. E will be what? E1 cos theta plus E2 cos theta. Got it or not? So can we write 2 E1 cos theta? Yes. Why not? Because E1 is equal to E2. And what is the value of E1? KQ by R square plus A square. Okay, what is cos theta? Now cos theta is what? If you see here, base upon hypotenuse. So cos theta can be written as A upon root R square plus A square. Base upon hypotenuse. So what we can do is that cos theta is A upon root R square plus A square. So E will be K again Q into 2A. You are getting it or not? Or R square plus A square to the power what 3 by 2. And Q into 2A is again what P. So K P upon R square plus A square to the power 3 by 2. Q into 2A is, remember always it is P, dipole moment. Everything is written here in the form of dipole moment. So E will be finally 1 upon 4 pi epsilon naught P R square plus A square to the power 3 by 2. So this is the general electric field on which line? Equatorial. Now for a short electric dipole, again we talk about the for a short dipole. Now short dipole, all of you got it. A is less than what? R. So A square is neglected. So what we see is 1 upon 4 pi epsilon naught P R22 cancel हो जाएंगे. P by what? It is simply R cube. So this is the conclusion. Here also E is inversely proportional to R cube. And you know, from axial and equatorial, what we calculate is that E axial by E equatorial is 2:1. You just see that it was axial was twice 2p by r cube. It is single. So E axial by equatorial 2:1 for short dipole. So these three derivations: potential energy of dipole, electric field intensity on axial line, electric field intensity on equatorial line. All three derivations are very important. Prepare them and thank you. Continuously watch my videos.